Class number 12, Sound in Periodic Structures. The word pyramid brings this image to mind. Ever heard of this singing pyramid? These, though impressive and majestic, will not be singing for you. However, in the other side of the world, there's a place called Chichen Itza. Here, the Mayans built a pyramid not as huge as that of Cheops, but one that, among other curiosities, can sing. Nah, not as mariachis, but as a bird. This is the Kukulkan Pyramid at Chichen Itza. While standing in front of it, if you clap, the echo that comes back sounds like this. Does not sound like a clap at all, right? But like a chirp of a bird. Not just like a chirp of any bird, but that of the quetzal, the sacred bird of the Mayas. It sounds like this. Here's the echo again.
Wow.
No one knows how much physics the Mayans knew when they built that pyramid back in the 11th century. But for explaining those echoes, we are going to need concepts and tools that Europeans did not develop until the 1800s. Let us start by watching the acoustic pressure waveform of a hand clap. Here's the frequency composition. A hand clap excites sound waves with a bunch of frequencies that peak between 500 and 1000 Hertz. A hand clap in front of a flat wall reflects an echo with an identical frequency composition. In other words, the echo will also sound like a hand clap. Assume that the clapper is at a distance d far away from the wall. And then we create a step of size s, much smaller than d, on it. Now let's focus on the area nearest to the step. Going back to the Huygens principle, the incident sound wave from the clap generates secondary sources on the wall. The ones in blue were excited at a later time equal to s over c, where c is the velocity of sound in the air, 1125 feet per second. A listener far from the wall will hear the sound from the blue sources superimposed to the yellow ones, but delayed twice the s over c time. If s is an odd multiple of the quarter wave, then the blue and yellow waves will interfere destructively, while if s is a multiple of the half wave, then the interference will be constructive. Those spectral components for which s is an odd multiple of the quarter wave will not be heard, while if multiple of half waves, their amplitude will double.
You said double, but that's 4 times.
Because that's a relative intensity chart, which goes with the amplitude squared.
Sebastian, that answer is better than the one I was about to give him. You're making it very difficult for me to like you. Let's go on. If we apply this response to the stimulus of a hand clap, we get the spectrum of the echo. This echo will certainly sound different than the originating hand clap. But it gets better. With 8 steps, those frequencies in which s is an integer multiple of lambda over 2, the amplitudes of all second sources will add, rendering 64 times the intensity of a single step, while those in which s is an odd multiple of lambda over 4 will cancel each other. The echo response now looks like this. then the frequency response to a hand clap would be something like this. But wait, the spectrum has become a discrete one, where all the components are integer multiples of the first. Does this ring any bells?
Music?
Yes, music. This is the spectrum of a periodic sound, like the notes produced by musical instruments or vocal cords. Those steps have turned that pyramid into a singing pyramid.
And now the one-note samba by the singing pyramid. Da 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 da.
Your silly joke actually makes a good point. A single note cannot explain the bird chip sound we heard. But that was just the sound of the first 8 steps, and the pyramid stairs have 91. The steps we have been considering are those at the base of the pyramid, which are at the same level as the clapper. But what about those at the top? The path of the sound will not only be longer and delayed, but inclined. Being inclined, now the interference will happen between secondary sources that are not just s feet away, but s primed feet away. A little trigonometry, and the expression for s primed comes out as s prime equal s by square root of 2 by the cosine of 45 degrees minus alpha. So s prime goes from s to s by square root of 2. Since s primed is always greater than s, then the frequency of its periodic echo will be lower. Say alpha equals 30 degrees. Then s prime is approximately 1.4 feet. And the frequency of the echo is reduced in the same proportion. That is from 655 Hz to 467 Hz. Not only the frequency of the echo from the top steps of the pyramid is lower, but it's also delayed. We may calculate the delays after knowing some dimensional data. And of course, a little trigonometry. That way, d sub top equals 79 feet divided by the sine of 30 degrees, which is of course 1/2. And that comes out as 158 feet. While d sub base would be 79 feet over tangent of 30 minus 79, and that equals 58 feet. The echo from the base will arrive at t sub base equal 103 milliseconds. The echo from the top will arrive at t sub top equals 281 milliseconds.
Isn't that d sub top the hypotenuse?
No, it is the gyrophotenuse.
Come on, give him a break. It was just a slip of the tongue. Yes, it is the hypotenuse.
Then that d sub base could have been calculated when multiplying whatever other you think by the cosine of 30 degrees minus 79, right?
Let's see. D sub base equal 158 by cosine 30 minus 79, and it comes to 58 feet. Yeah, you're right. For a clapper standing 58 feet from the base, the echo starts at 103 milliseconds after the hand clap. Due to interference with the steps, the echo will return with a periodic sound of 655 Hz, or an E5 in musical terms. As echoes keep arriving from higher and farther steps, the frequency will go decreasing. The last part of the echo comes from the top steps, 281 milliseconds after the clap, with 467 Hz or an A#4 in musical terms. That is 3 full tones below. And that sounds quite like the chirp of the quetzal that pitches from high to low around those tones. There's more about sound in periodic systems.
What? More pyramids?
No. We're done with pyramids. But here's another interesting case. Say there's someone that needs to address a group of people, but not having a speaker with enough power and being an ignorant in acoustics, tried using 8 low-power ones in a totem pole arrangement. His audience is about to become a victim of what in an audio engineering jargon is known as comb filtering. Here's what's being said.
Hello everybody, it's Mr. Gaff here, and today we are going to be talking about parts of speech.
But here's what's heard.
Hello everybody, it's Mr. Gaff here, and today we are going to be talking about parts of speech.
To explain this effect, let us concentrate on the first 2 speakers and the sound path to the listener. If the path difference delta p is an integer multiple of the sound wavelength, there will be constructive interference, that is shown in green, while if it's an odd multiple of half waves, there will be destructive interference, that are being shown in red. The effect of being 8 speakers has the same effect on the frequency response as the multiple steps of the singing pyramid. Someone thought the chart looked like a comb, and the name comb filtering stuck. That's why stacking speakers in such a way is not advisable. To avoid comb filtering, sound power should come from a single point source.
Pyramids? Well, okay. Wow. And now this is a nuisance. Are these periodic systems good for something?
There are things in life that are just nuisances, but we still need to know about them, right? However, this is not the case. Listen on. Electronics gets its name from the vacuum tube technology of its origins back in the early 1900s. By mid-century, it evolved into electron hole motion in semiconductors. And then it began processing signals using all sorts of effects, including sound. A frequent task in electronics is that of processing a signal that is sharing the frequency spectrum with other signals and the omnipresent noise. Selecting by frequency is called filtering. For example, filtering is needed for the modulating the signal of, say, WYQR, a music FM station that broadcasts from Miami, Florida. All FM stations lie within the VHF band, which stands for very high frequency. The VHF band goes from 30 to 300 MHz, but the FM band only from 88 to 108. And within, there's a small slice of 0.2 MHz centered at 105, where the WYQR is allowed to insert its signal. To listen to this station, the electronics in the radio must filter everything else away and isolate the station's signal. The inductor capacitor circuit resonator is the most common filter circuit for radio in the lower channels of TV. But it gets messy as the frequency goes into the hundreds of megahertz, where coils must be reduced to 1 or 2 turns, and maybe some fraction. There's another problem. This is a cellulophone printed circuit. Where would you squeeze a coil in here? That is when the SAW filter or surface acoustic wave filter comes to the rescue. Here's what it has inside. IDT stands for interdigital transducer. The input IDT excites a sound wave that is picked up by the output one. When there's no signal, there's no expansion or contraction of the crystal lattice. But if an electric field appears, it happens. Since it alternates, a pressure wave is excited.
Why only to the right?
There's also one to the left, but for now, we will let that one be absorbed at the end of the ship. But wait, I have a question for you. You wondered about the direction, but why not the wavelength?
That was just an example, right? Any other wavelength would have been just as good.
This is a periodic structure, like the pyramid stairs or the speaker stack. The depicted wavelength is the most favored, for it interferes in a perfectly constructive way. The output also adds to the selectivity, for it is also a periodic system. Only that wavelength will match the interdigital transducer periodicity. Here's the frequency response of a commercial SAW filter. Its center frequency is about 1.5 gigahertz. Notice that if the signal shifts from that frequency only 2%, the output power drops more than 5,000 times, or 37 dB. SAW filters are not only dramatically smaller and far more selective than their LC counterparts, but do not require tuning and can be mass-produced. So yes, periodic sound systems are very good for this. With the SAW filter, we have encountered periodic systems in the micrometer range. What would be the ultimate periodic system? It would be that of the atoms in a crystal, only that periodicity at this level is in the order of 10 to minus 10 meters. Being the speed of sound in, say, silicon, about 10 to 4 meters per second, the frequency with wavelength in the range could be in the order of 10 to the 13th hertz, that is tens of terahertz.
Can we excite sound waves with such frequencies?
You mean like we did with the SAW filter? Short answer is no. However, those sound waves are always bouncing around within any crystal at room temperature. Together with the kinetic energy in the chaotic motion of free charge carriers and the electromagnetic radiation, it makes up the thermal energy of the crystal. Atoms in a lattice may be modeled as this, where each atom is a harmonic oscillator. But at atomic levels, quantum mechanics takes over, and the oscillation energy cannot just have any value, but a discrete set given by this equation where h is the Planck constant and f the frequency. In a crystal at a temperature T, there are many sound waves with frequencies and energies of that allowed set bouncing around it. Those sound waves with energies proportional to its frequencies are called phonons and have a particle behavior same as their cousins of electromagnetic radiations, the photons. How many of each level? That will be the distribution, the Bose-Einstein distribution. Particles that show such energy distributions are called bosons.
Like the Higgs boson?
Yes, but photons are also bosons, as well as a bunch of other elementary particles like the gluons, mesons, the W, the Z, and the hypothetical graviton.
Never heard of those. What about electrons?
Those are leptons, which have a different energy distribution, the Fermi-Dirac distribution. That is why they're called fermions.
Why are those leptons so different?
Fermions are subject to the Pauli exclusion principle, meaning that no two particles may share the same energy level. That is why, if there are n fermions at 0K, they cannot all be at the same minimum energy level like the bosons, but must accommodate into the first n energy levels.
Isn't it time for the quiz?
Sorry, I just got carried away. It is. Well, it's that time. Time for the quiz. Here the answers will follow the question or problem, but hit pause and try answering it first. Question number 1. Which better describes the echo for that clapper? A. Strongest echoes arrive during the clap, but a 463 Hz sound can be heard as it fades away. Could be. B. The echo is not periodic because that only happens if the clapper is far away. Yeah, there was something about that. C. Nearness echoes back only the higher pitched sound, 655 Hz. I think that was so, yeah. D. That near, you can hardly see the steps, so no echo can bounce back. Oh my God, no echo. Okay. Make your pick. A good line of thought will go like this. Let me check on D first. Since if there's no echo, then I don't have even to consider A, B, or C. It is true that being so near, I could hardly see the steps. However, the wavelengths of sound in the echo is larger than the size of the step, so there will be a lot of diffraction, which is not happening to the light I see. Sound rays will be bending at every step, so echoes could be heard. D is out. How about B? If the echo is not periodic, then there can be no single frequency, and that would eliminate A and C. It is true that the path only has regular increments if sound rays could be assumed to be parallel, and that only happens for faraway clappers. However, the only steps that are near are just a few at the bottom of the stairs. Most of the steps are far away, which are the ones whose echoes will be better heard. B is out. Now I must decide if the echo has the highest pitch or the lowest. It is true that if the clapper is far away, the echo coming from the nearest steps has the highest pitch. However, it's not for being near, but for being less inclined. The more inclined, the larger the path increments, and thus the lower the frequency. Be in this case the one with the maximum inclination, the answer is A. Question number 2, actually 3 questions. Subway musicians are frequent victims of comb filtering. Say the sound is being produced 1.5 feet from the wall. A. Which is the lowest pitched note with destructive interference for a listener standing in front several feet away? B. Which is the lowest pitched note with constructive interference for that listener? And C. Can the fiddler hear the problem? Here's my answer to question A. The path difference for that listener will be twice 1.5 feet. So the interference to be destructive, the halfway must be 3 feet. Being the speed of sound 1125 bits per second, a 6 feet wavelength corresponds to a frequency of 187.5 Hz. That is near to an F sharp 3. The answer to question B? For constructive interference, the 3 feet must be at least 1 full wavelength, and that corresponds to twice the above frequency, or 375 Hz, which is the same note in the next octave, F sharp 4. Here's the effect of the comb filtering on the spectrum of the fiddle. Here's a detail. And here's the answer to question C. He would not be aware of it, for his ears are so near to the sound source that the interference with the reflected wave from the wall will hardly be noticeable. Not so for the listener standing a few feet away from both the fiddle and the wall. Question number 3. Some saw filter designs, instead of wasting the wave going in the wrong direction, introduce reflectors, which are just shorted IDTs. Below there are 3 explanations. Find the best one. A. Shorted IDTs cannot take power from the wave. Since energy does not disappear, it must be reflected. B. The shorted IDT aluminum contact works like the rebar in concrete. It increases K, so it reflects. And C. No interdigit electric field can exist under the shorted IDT, and that allows no expansions or compressions. The effective acoustic impedance has gone way up, like a hard wall, hence reflection. Now make your pick. Let's say A. The fact that it cannot take power from the wave does not necessarily imply reflection. It could just propagate through without any power being taken from it. So this is out. Now B. Aluminum over a piezoelectric ceramic is like butter over a week-old hardened bread. It has no effect on the acoustic impedance. So this is total BS. So that leaves C as the best explanation. And problem number 4. Prove that the internal energy of a silicon crystal at room temperature, doped with 10 to 19 phosphorus atoms per cubic centimeter, comes mostly from phonons. Don't worry, there's a hint. Do it by proving that the contributions of electrons is only 10 to minus 4 of the total, and that of photons is even less, approximately 10 to minus 8. Just kidding. The facts are true though. A limiting factor in determining the capacity, performance, and speed of computer chips is thermal transport, which rides not on electrons or photons, but on phonons. There's still one last class in this course about the physics of sound, and it deals with the case in which the source and the listener are in relative motion. It becomes kind of dramatic when the source speeds faster than sound. Subscribe to the channel.